Now in section 13.2, here's the idea. If we conclude that at least one of the means is different from the others, then the next logical question is, how are they different? So if we conduct an ANOVA test and if we conclude that the null hypothesis is correct, then that would mean that all of the means are equal. So if we conclude that all of the means are equal, then we're done. They're all equal. But if we reject the null hypothesis and conclude that at least one of the means is different, then the next logical question is, how are they different? And so to answer that question, how are they different, we're going to conduct what is called a post hoc test on a one-way ANOVA. So when the conclusion of a one-way ANOVA test is that at least one population mean is different than the others, it is logical to then investigate how the means differ. To do this, we make additional comparisons between the means using techniques called multiple comparison methods. We will use the Tukey test, which is also called the honestly significant difference test and the wholly significant difference test. So we're going to call it the Tukey test, named after John Tukey, the statistician. So what is the Tukey test? The computation of the test statistic for Tukey's test for comparing pairs of means follows the same logic as the test for comparing two means from independent sampling, but the standard error that is used is, so the standard error, in other words, that means like the standard deviation, is equal to, and it's going to be abbreviated SE, so that's going to be our notation, and that's going to equal the square root of S squared divided by 2 times 1 over N1 plus 1 over N2, where S squared is the mean square error estimate, or the MSE. So keep that in mind. In this calculation right here, S squared is going to be the mean square due to error that we calculate in our ANOVA test. So again, S squared is the mean square error estimate, or MSE, of sigma squared from the one-way ANOVA. N1 is the sample size from population 1, and N2 is the sample size from population 2. So what I mean by this is that what we're really going to be doing is we're going to be comparing pairs of means at a time, and we're going to be using this for the standard error in the calculation. So the test statistic for Tukey's test. The test statistic for Tukey's test, when testing, the null hypothesis is going to be that mu1 equals mu2, so the mean of population 1 equals the mean of population 2, versus the alternative hypothesis, mu1 does not equal mu2, so the mean of population 1 does not equal the mean of population 2. And what we're going to do is we're going to be doing this for each possible pair of means. So we're using 1 and 2 here, but we could also be comparing mean 1 to mean 3, or mean 1 to mean 4, or mean 2 to mean 3, or mean 2 to mean 4, and so on. So all of the possible pairs we're going to be looking at. Anyway, the test statistic is given by Q naught. So Q is our test statistic. Q naught is equal to. Now what we're going to do is we're going to find the differences between the sample means. So X bar 2 minus X bar 1 minus mu2 minus mu1 over this standard error calculation that we had up here. So over SE. Now, if mu2 and mu1 are assumed to be equal to each other, then mu2 minus mu1 would be 0, which means we really don't need that in the calculation. So really what we're going to be doing is just looking at the difference between the two means, and we're going to divide that by the SE. And again, that right there is just what we talked about up here. So again, that's the mean square due to error divided by 2 times 1 over the first sample size plus 1 over the second sample size square rooted. Now we are going to always arrange this so that the larger sample mean is in front and the smaller sample mean is in back. So X bar 2 is going to be bigger than X bar 1. And again, we're just looking at pairs, so it doesn't really matter, but we always want this to be the bigger number in front, the smaller number in back. So this test statistic is always going to be positive. Again, S squared is the mean squared error estimate, or the MSE from the ANOVA. N1 is the sample size from population 1, and N2 is the sample size from population 2. Now, the Q test statistic follows a studentized range distribution. The shape of the distribution depends on both the error degrees of freedom, which we're going to denote by this symbol, looks sort of like a funky V, and the number of means being compared, K. We will compare the test statistic Q0 to a critical value from this distribution, and the critical value is going to be denoted by Q sub alpha VK, where alpha is the level of significance of the test, which is the probability of making a type 1 error. So just like any other hypothesis test, we're going to have a level of significance, alpha. And so again, the Q is going to depend on what the level of significance is. It's also going to depend on what the degrees of freedom due to error are, which again is denoted by this V symbol, and then the number of categories that we have, which is going to be denoted by K. The level of significance alpha is called the experiment-wise error rate or the family-wise error rate. So like for these problems, it's going to say, instead of saying use a level of significance of alpha, it's going to say use an experiment-wise error rate or use a family-wise error rate. So that's alpha, which is still the level of significance. It just has a different name for the Tukey's test. Now, the critical value for Tukey's test. The critical value for Tukey's test using a family-wise error rate alpha is given by, again, Q sub alpha VK, where V is the degrees of freedom due to error, which is the total number of subjects sampled minus the number of means being compared, or N minus K, the total number of data values minus the number of categories. And K is the total number of means being compared. It's the total number of categories. Use table 10 to find the critical value from the studentized range distribution with V equals 21 and K equals 3, with a family-wise error rate of alpha equals 0.05. In other words, we're going to find Q sub 0.05, comma 21, comma 3. So if you look in the appendix of the textbook, table 10 starts on page A20 and goes through page A23. Really, what we have here is two different tables. So the first two pages have to do if we have a family-wise error rate or a level of significance of alpha equals 0.05. We have different possible values for V, and then we have different possible values for K along the top. The last two pages, pages A22 and A23, is if the family-wise error rate is 0.01. And again, we have different values of K and different values of V. So for this particular problem, we want to find, again, Q sub 0.05, 21, 3. So our family-wise error rate is 0.05, so we're going to use the first two pages of the table. Now, again, we have V equals 21. So that means I'm going to go down this column to find V equals 21 and K equals 3. So I'm going to go across to find where K equals 3. Now, in this particular case, if V equals 21, if I go down this, I don't have an option for 21. I have an option for 20. So when that happens, I'm going to go with what's closest. So my closest option to 21 is 20. So I'm going to use that. I'm going to go over to where K equals 3. That's over here. And so my critical value would be 3.578. So Q sub 05, 21, 3 is going to be approximately 3.578. So once again, our table hasn't got the most detail, so we don't have 21 degrees of freedom due to error, and so we have to go with 20 in this particular case. And then we do have the k equals 3, so that's where we get our 3.578 critical value. Now, if you look, if v equals 24, the critical value would be 3.532, and notice there's not a lot of difference between those two. If we did have a row for v equals 21, the value would be somewhere between 3.578 and 3.532. It would be something in between there. Now, if we want to conduct Tukey's test, so after rejecting the null hypothesis that mu1 equals mu2 and so on, use steps 1 through 6 to compare pairs of means for significant differences. So again, what we're going to do is we're going to, if we've rejected that the means are all equal and we've concluded that at least one mean's different, then we're going to look at each pair of means in order to see which ones are different. And so for each pair of means, we're going to calculate this test statistic Q0. So step 1, we're going to arrange the sample means in ascending order. Now, the reason why we're doing that is because, remember, when we subtract, we want to have the larger X bar in front and the smaller X bar in back. So we are just arranging them in order so that we don't accidentally subtract them in the wrong order. Step 2, compute the pairwise differences. So for each pair of means, we're going to take the larger mean minus the smaller mean and figure out what that difference is. So again, this is denoted as X bar I minus X bar J, where X bar I is the bigger of the two. So X bar I is bigger than X bar J. Step 3, we're going to compute the test statistic. So again, we're going to calculate Q0. So that's going to be the difference we just found in step 2. So X bar I minus X bar J divided by the SE. So again, that's going to be the mean square due to error divided by 2 times 1 over the first sample size plus 1 over the second sample size. Now, if the two sample sizes are the same, then that's not going to be a problem. But if we have different sample sizes, we do have to pay attention to what those are. So we're going to do that for each pairwise difference. Step 4, we're going to determine the critical value, or the Q sub alpha VK, where alpha is the level of significance or the family-wise error rate. We're going to compare each of our test statistics to that critical value. If the test statistic is greater than or equal to the critical value, we're going to reject the null hypothesis that mu sub I equals mu sub J. So we're going to reject that that pair of means are equal, and we're going to conclude that those two means are significantly different. Step 6, we're going to compare all pairwise differences to identify which means differ. So in other words, step 6, we're going to kind of summarize. Now, this will make a lot more sense when we look at an example. So in the examples from the previous section regarding the consumption of calcium for children who exclusively use lean meats, mixed meats, or higher fat meats, we rejected the null hypothesis that the mean of lean meats equaled the mean of mixed meats and equaled the mean of high meats. So we rejected that this was true, and we concluded that at least one mean was different from the others. Use Tukey's test to determine which pairwise means differ using a family-wise error rate of alpha equals 0.05. So I'm going to write down some of the information that we found previously. So back from section 13.1, right off the bat, we found that the X bar for the lean meats was equal to 794.7625. X bar for the mixed meats was 898.5375. And X bar for the higher fat meats was 829.2375. So I'm going to just write those down here, and I'm going to write those in ascending order. So X bar for the lean meats is the smallest, and that's 794.7625. X bar for the higher fat meats is the next smallest, that's 829.2375. And X bar for the mixed meats is the largest, it's 898.5375. So that's step one. I have arranged the sample means in ascending order. Now I'm going to compute the pairwise differences. So if I take, and I'm going to do that, by the way, here. I'm going to do that here in this table that I've organized. Now I want to explain what I've done here with this table. So what I want to do is I want to make a comparison for each pair of means. So I'm going to compare lean meats to mixed meats. I'm going to compare lean meats to high fat meats, and I'm going to compare high fat meats to mixed meats. So there are 3 different comparisons that I can make with the means. Again, compare this mean to this mean, this mean to this mean, and this mean to this mean. So that's what I'm going to do. If we had 4 means, you have to look at all of the possible comparisons that you could make. And so if you have 4 means, there's going to be a lot more of options that you have to compare. So if I compare mixed meats versus lean meats, now mixed meats has a larger mean, so we're going to put it in front and subtract. So I'm going to take 898.5375 minus 794.7625. And if I do that, 898.5375 minus 794.7625, that's a difference of 103.775. Again, that's the difference between mixed meats and lean meats. If I compare mixed meats with higher fat meats, so mixed minus high, I'm going to do that here. So that's going to be, again, mixed meats in front because it's larger, 898.5375 minus 829.2375. So 898.5375 minus 829.2375, that is 69.3. And last but not least, I'm going to compare higher fat meats with lean meats. So that's going to be a difference of 829.2375 minus 794.7625. And 829.2375 minus 794.7625, that is a difference of 34.475. Now, what we're going to tell is, are those differences statistically significant? So is this difference statistically significant or not? So to make that decision, I'm going to have to calculate each test statistic. So I'm going to have to calculate Q naught. Now, the way we calculate that test statistic, again, is we take the difference and we divide that by the square root of S squared divided by 2 times 1 over N1 plus 1 over N2, or Ni and Nj. Now remember, the S squared is the MSE. So S squared equals the mean squared due to error, and we calculated that back here. The mean square due to error is equal to 1,432.6093. We calculated that when we did the ANOVA test. So that is, again, 1,432.6093. 0.6093. That's the mean square due to error. So if I want to calculate Q naught for our first pair, again, comparing the mean of mixed meat to the mean of lean meat, if I want to calculate Q naught, then that's going to equal the difference. So that's 103.775 divided by the square root of S squared, which is the mean square due to error. So that is 1,432.6093 divided by 2 times 1 over the sample size for mixed meat. Now, in this particular case, all three sample sizes were the same. They're all 8. So the number of data values for lean meat equals the number of data values for mixed meat equals the number of data values for higher fat meat, and all of those are 8. So I'm going to just constantly be using 8 for the N here. So this is the number of data values from mixed meat and the number of data values from lean meat. So if I want to calculate this test statistic, I do have to be careful how I type this in my calculator. So I'm going to take 103.775 divided by the square root of, now again, under this, I've got to be careful, 1,432.6093 divided by 2 times parenthesis 1 divided by 8 plus 1 divided by 8 close parenthesis. And that is 7.755 if I round to 3 places. 7.755. I'm going to do the same thing for the other 2 pairs. So for the second pair, and that is comparing mixed meats to high-fat meats, this is all the same except the number on top is 69.3. So 69.3 divided by the square root of 1,432.6093 divided by 2 times 1/8 plus 1/8. And again, it's both 1/8 again because the sample sizes are all equal to 8. Technically here, this is the sample size for mixed meats, and this is the sample size for higher fat meats. But again, because they're all 8, that makes this easy. So if I punch this in, 69.3 divided by the square root of 1,432.6093 divided by 2 times parenthesis 1/8 plus 1/8 close parenthesis. And so that is 5.179 if I round to 3 places. 5.179. And last but not least, I'm going to do the same thing for the comparison of higher fat meats with lean meats. So for that, Q naught is going to equal our difference, 34.475 divided by that SE. So again, divided by the square root of 1,432.6093 divided by 2 times 1/8 plus 1/8. Again, this is technically the sample size for higher fat meats. This is the sample size for lean meats. But again, in this case, everything's 8 in terms of the sample size. So 34.475 divided by the square root, 1,432.6093 divided by 2 times parenthesis 1/8 plus 1/8 close parenthesis. And so that is 2.576 if I round to 3 places. So now I need to make a decision. Do I reject that the two means are equal, or do I conclude that they are in fact equal? Do I not reject that they're equal? Well, in order to make that decision, I need to find my critical value that I'm going to compare these test statistics to. So in other words, I need to find my Q sub alpha. So I need to find my Q sub 0.05, comma, 21, comma, 3. So I need to use this value that we found up here. So that is 3.578 approximately. Now remember, we had to use 20 instead of 21. So I'm going to compare my test statistic to my critical value that we found up here before. And again, this is coming from the fact that we had 21 degrees of freedom due to error, and that's coming from 24 minus 3. And we had 3 different categories that we were comparing. So again, our V in this particular case is 24 minus 3, which is 21. Our K is 3. And so again, this is the critical value that we found before. So if the test statistic is larger than 3.578, we reject the null hypothesis. So in this particular case, because 7.755 is bigger than 3.578, we reject the null hypothesis. And the null hypothesis is that the mean of mixed meats equals the mean of lean meats. So we're rejecting that mixed meats equals lean meats. So our conclusion is that the mean of mixed meats does not equal the mean of lean meats. And again, that's my conclusion because our test statistic is bigger than our critical value. Similarly, for mixed meat versus higher fat meat, because the 5.179 is bigger than the 3.578, we're going to reject the null hypothesis that the mean of mixed meats equals the mean of higher fat meats. So in other words, our conclusion is that the mean of mixed meats does not equal the mean of higher fat meats. Now, for the third comparison, 2.576 is smaller than the critical value of 3.578. So because 2.576 is less than the 3.578, we do not reject the null hypothesis that the two means are equal. So our conclusion is that the mean of higher fat meats equals the mean of lean meats. So looking at this again, it would appear that the mean of lean meats and the mean of higher fat meats are equal, but neither one of those equal the mean of mixed meats. So our conclusion is, our overall conclusion is that the mean of lean meats equals the mean of high fat meats, but that does not equal the mean of mixed meats. So the mean of mixed meats is what's different. So again, these two aren't equal. So lean meat doesn't equal mixed meat. High fat meat doesn't equal mixed meat, but lean meat and high fat meat are equal. So these two are equal, but neither one of them equal mixed meat.